Okay, we are on, thank you. We're on chapter 2 here. Now the internet woke up. Last time we got into sort of the Bohr model, and then we kind of got into the quantum mechanical model of the atom, and that led us to quantum numbers. And there's four quantum numbers that we were talking about. There is the n, which is the principal quantum number. N runs from 1 through 7. It's basically, for all intents purposes, sort of your energy levels. And again, n equals 1 is the ground state. So the lowest energy is the closest to the nucleus. We also have L, which is the angular momentum, or the angular, I'm sorry, quantum number. And L has values of 0 to n minus 1, all whole numbers sort of going that way. For the most part, it tells you essentially the type of orbital that you are sort of dealing with. Um, for example, last time we saw if we have an L value of 0, that represents basically an s orbital. If you have an L value of 1, that's the p orbital, and so forth. So that essentially will kind of tell you that. We have the magnetic quantum number here, m sub L, and that is values of minus L to 0 to negative L. So for example, if we took our 1 here, which represents that we have basically a p orbitals, the m sub L for that 1 would be minus 1, 0, and plus 1. Each of those basically represents the orbitals in three-dimensional space. And also, if you want to just think about it in a sense, it represents how many orbitals you have for that particular type of orbital. Here, there's basically three numbers, which represents the three individual p orbitals that's in a p subshell, like your px, your py, and your pz. And lastly, we have a spin quantum number, which is either plus or minus a half. And basically, when electrons go into the orbitals, they will either sort of spin upwards, if you will, sometimes represented with an arrow pointing upwards, and that would be a plus a half spin. Plus a half. And if it's sort of spinning in the downward direction, that would be basically minus a half in terms of the spin quantum number. So these four quantum numbers basically are really the basis, as we got into a little bit last time, sort of electron configuration, and why, again, there are only certain orbitals, for example, allowed on certain energy levels, and, sort of where we get all those sort of orbitals that we put in there. Remember, orbitals are really just probability mass or theoretical sort of ideas, which in an atom, where you could find an electron with some high density of electron density. Remember, we moved to those guys as opposed to sort of Bohr's model, which was orbits, where we have these for sure sort of orbits where electrons are and the sure patterns at how they're moving, to this idea of the quantum mechanical sort of model with like Heisenberg's uncertainty principle and so forth, that we don't really know how a particle like an electron is actually moving. And the more we know about, for example, how it's moving, the less we know, for example, of sort of its location, and vice versa. The more you know about sort of its location, the less you know about how it's moving. So the best we could do is get us these sort of probability maps. So as we saw before, and we went through 3, I think, n equals 1. The only acceptable value for L would be 0, as it's n minus 1, and 1 minus 1 is 0. That means that we would only have basically one s orbital, and we could put in there, in terms of electrons, 1 up and 1 down. And that again means on our first energy level, we basically have a 1s orbital. On the second energy level, as we did, we can have L values of 0 and 1, as n minus 1 is 2 minus 1, which is 1. Again, the 0 here represents the s orbital. And again, the 1 value for an L represents basically the p orbitals. And for each of these sort of L values, for our L is equal to 0, we could have an m sub L, which would equal 0. For our L that's equal to 1, we could have an m sub L of minus 1, 0, and plus 1. Once again, what that essentially tells us is when we get to the second energy level, we still have s orbitals, again represented as a 2s orbital. And that is where we first start to see our p orbitals basically appear. And we do have 3p individual orbitals represented by each of these numbers. And in any of these here, you can basically put an electron either kind of going upwards or downwards. When I think we finished up on 3, where again values of L could be 0, 1, or 2, as 3 minus 1 is 2. Again, this represents an S, this represents a P, and that is why we do not see d orbitals basically start to appear until the 3rd energy level, and that is what the 2 represents. If you went through the M sub L for 0, it'd be that. If you went through the M sub L for 1 on that level, it'd still be those guys. So if I did my L is equal to 2, my M sub L would equal -2, -1, 0, +1, +2. And once again, as you may be familiar with, as we talked about, there are 5 different d orbitals, and each of them are represented by one of those numbers. And that's what we know when we get to this 3rd energy level. Again, we have an s orbital still available. We still have p orbitals available. And again, this is where we first start to see our appearance of our d orbitals. Any questions on any of that there? All right, so let's just roll through n equals 4 just for fun of it. So for n equals 4, we can have L values of 0, 1, 2, and we could also have an L value of 3 on that energy level. Again, n minus 1 in this case is 4 minus 1, which would be 3. What that essentially tells us when we look at it is on the 4th energy level, we still have our s orbitals, we have our p orbitals, we have our d orbitals, and this again is where we first start to see our f orbitals start to appear. And we could go through the M sub L for each of these. So for this guy, again, it would equal 0. For this guy here, the M sub L would be -1, 0, +1, which again is our 3 p orbitals. As we did on the previous page, this guy would be -2, -1, 0, +1, +2. Those are our 5 d orbitals. And now here for our M sub L for 3, -3, -2, -1, 0, +1, +2, +3. Dare I count those numbers? 1, 2, 3, 4, 5, 6, and 7. And again, that is why we have 7 f orbitals available to us on an energy level. And again, the M sub s here, obviously for any of those orbitals would be plus or minus 1/2. So again, based on quantum numbers, f orbitals cannot appear before the 3rd energy level, just like d orbitals cannot appear before that 3rd energy level, p orbitals before the 2nd. So again, if we kind of go through our little arrangement here, we have our 1s, our 2s, and our 2p, our 3s, whoops, 3p, too many, and again our d. And again, we get to our 4th energy level. Now we have our 4s, still our 4p, our 4d, and now our 4f basically starts to appear. Energy is obviously increasing this way, and we're also getting further away from the nucleus as we continue up sort of our energy levels. Electrons are essentially filled from lowest energy levels to highest as well. Now, we talked also maybe about a couple of terminology, but just in case we didn't, for example, if I want to know how many maximum electrons to fill the following, the n equals 3 level or shell, the 3d subshell, and a 4f orbital. So take a moment and decide how many electrons to maximally fill each of those things. So take a moment, see what you come up with. Yeah. The question is, if I wanted to fill up each of these with the maximum number of electrons, how many electrons could I do in each? in each of these individual things here. That's 3, I guess, comes after 4 or 2. So for each of them, you want to fill up the n equals 3 level, the 3D subshell, and a 4f orbital. So 60 is incorrect for sure. Yeah. So we'll talk about it in just a second. Okay, so let's talk about then, if I did want to fill up the entire n equals 3 level or shell, how many electrons can I put in there? What do you think? 36? Okay, so let's see. So the n equals 3 level or shell, when we talk about a level or shell, some books use shell, some people use level. They're talking about every single orbital that is found on a particular energy level. So if we're talking about the n equals 3 level here, we're talking about all those individual orbitals. As we talked about last time, each individual orbital could only hold 2 electrons, just like kind of electron configuration. So that would be 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons would max out that entire energy level if you filled up all the orbitals with electrons. Question on that there. Yeah. Yeah, no, so we're talking about specifically just that energy level, just fill up that energy level. Not to get there, for example, but if we, how many can we maximally put on that particular energy level? Yeah. Other questions? How about the 3D subshell? How many electrons can we put in there? It is 10 because now we're talking about a subshell or a sublevel. And when we talk about a subshell or a sublevel, as we talked about last time as well, that is basically a grouping of the same type of orbitals on the same energy level. So that would be all those guys right there. And that is, again, 2 in each, and there's 5 of them. That would give you 10 electrons if you filled up the 3D subshell. I'll go 10 electrons there. How about a 4f orbital? How much is that? So 14 would be if I took them all, right? But then it would be asking not an orbital, but it would be asking a subshell or sublevel, right? So an orbital, an individual f orbital, basically is what it's asking, could be any of these boxes here pretty much. So any box could hold basically 2 electrons total, and you would max out at 2 electrons. Now, if the question asks how much to fill up the 4f subshell, the answer then would be 14. Yeah. So again, you got to be careful sometimes with the terminology in terms of what they're asking. Now, you could draw this out and count up the electrons, but nobody really wants to do that. So there is sort of a quick way that you could figure out if you were just interested, for example, in how many electrons to fill up a particular energy level. You could use this formula of 2n squared. N is the energy level. You want to square it first and then multiply it by 2. So how this works is, for example, the one we just did, which was n is equal to 3. That is 3 squared, which is basically 2 times 9. That is 18 electrons, yeah, that you could put in there. So you want to take the energy level square first, then times by 2. That works very nicely in case you get to like the 6th energy level, right? You don't want to draw all that out and try to figure out, how much is going on there. So you can basically just take 6 squared, 36, and times it by 2, right? And that would get you your 72 that you can put in there. Right away, we talked about our energy levels here going into our, say, 4th energy level, right? And our 4th energy level, in this case, is where we start to see our Fs. What happens when we get to our 5th energy level and we have our Ls? Our Ls would then be 0, 1, 2, 3, and 4. We already know 0 is S, right? That is P, that is D, that is F. Are there orbitals above F? The answer is, based on quantum numbers, yeah, there's numbers, right? So it actually just goes alphabetical after F, so G and so forth after that. We never get to any of those with anybody on the periodic table, but in theory, they are, kind of available there. So it is possible, again, to have, there are other orbitals above F, and again, it just kind of goes alphabetical at that point, although you will basically tap out at the F over there on the periodic table. You really won't go past it in terms of orbitals. Any questions on that there? So the idea of quantum numbers, which you do need to know how to do here and obviously understand what they mean, are really the basis for what you did probably in the last class, which is just electron configuration and writing electron configuration. So why don't we talk about that while we're here? Electron configuration, right? Really, to write electron configuration, there's kind of two things that you need to know. You basically just need to know, S orbital could hold a maximum of 2 electrons. P subshell could hold 6 electrons maximum. D subshell could hold 10. And lastly, our F subshell can hold 14 electrons. You also need to know the order at which electrons are placed into the atom, and they're always placed into the atom lowest energy first to highest energy. That also means that you do need to know the proper sort of order, if you will, of our orbitals here. Now, the way I sort of drew this, not too bad-ish, straightish, I guess. This would be sort of what the energy of all the orbitals would look at like in something like hydrogen, which has just 1 electron. And what I mean by that is, as best as I drew it here, all of our orbitals on the second energy level are exactly equal in energy. All of our orbitals on the third energy level are equal in energy, and our fourth sort of equal in energy, and so forth. But what happens when you get a lot of electrons near each other, right? Electrons are negatively charged near other electrons which are negatively charged. Do they really want to be near each other? Not so much, right? So what we actually get when we get a lot more of electrons involved is there's actually a shift in the energy of these orbitals. And the major shift happens actually right around here between these two guys. The 4s actually is lower in energy than, say, the 3D, and that pattern sort of follows all the way through. And you do need to have sort of the correct order so that you can write the electron configuration correctly as they go in, again, lowest energy to highest. So in this case, again, they would kind of go here. This guy's actually lower than the 2p. They would go into the 2p, the 3s, the 3p, the 4s to the 3d. And again, like I said, that sort of follows. So there's one way that you could do it pretty easily, and you can make a little chart for yourself fairly easily to know the proper order. And really all you have to remember to make this chart for you is what we just talked about here with our quantum numbers, which is on the first energy level, right? The only orbitals there based on quantum numbers are the s orbitals. So you basically just need to write 1s up there on top. It's not until we get to the second energy level that we actually see the p's. So you would write down and to the right a little bit a 2p, because that's where we start to see the p's start. On the third energy level is where we see the d's start. Throw a 3d down diagonally there. And on the fourth energy level, that is where we see the F's basically start. So if you could just remember 1, 2, 3, 4, and the letters that go with it, you'll be able to basically make this chart, which is quite helpful. All you have to do at this point is, frankly, just put the same letter underneath and go 1 through 7 on most of them. So 1s, 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, I'll learn to count, 6d, 4f, and 5f. I'm actually just going to drop my 4f down just a little bit there. I think I made him a little too high there. Let's drop him down just a little bit there. And now what you have right now then is essentially the order at which electrons go into the atom that you created. And we always start up here at top, and we basically just follow the arrow, and we draw arrows like so, and just kind of zigzag back. And here you can see we go from our 3p to our 4s, and then into our 3d, and so forth, into our 5s, into our 4d, and so forth. You basically just continue following the arrows, basically. And if you know how to make this, and you know how this column here, you pretty much should be able to write any electron configuration that you would need to do by following basically this order. Any questions on that there? So what is electron configuration? It basically tells us how the electrons are placed into the atom. And let's write some electron configuration. So why not start with the simplest there, which is hydrogen. Hydrogen has an atomic number of 1, which means it has 1 proton. And because it has 1 proton, and if it's neutral, it has 1 electron in that case. So starting here, we're going to go to our 1s orbital. And our electron configuration would be 1s2. Now, the number in front is the principal quantum number, so that is the n number there. And that's basically the energy level, right? It's basically telling us we're on the first energy level. I'm sorry, I went too many electrons there. I got ahead of myself. I went all the way to helium. There's actually only 1 electron, so 1 would be a good number there. There we go. 1. The S tells us the orbital, our subshell that the electrons are in. So basically what this is telling us is on the first energy level, I'm hanging out in an s orbital, and the top number here, which is a superscript, tell us the number of electrons in the orbital or subshell. So basically what this is telling me is on the first energy level, I'm hanging out in the s orbital, and there's 1 electron hanging out in that s orbital. Any questions on that? And that is how you should write electron configuration. Regular size number on the front, lowercase letter, superscript up on top, number, no dashes, commas, other weird things people like put in there. Another way that we can represent electron configuration is what is known as orbital diagram. An orbital diagram is either using boxes or lines to represent the orbitals, and also arrows to represent the individual electrons that are present. So if we were to draw an orbital diagram here for hydrogen, we would roll maybe with 1 box or 1 line. This would represent our 1s orbital, and the electron goes in the upwards direction in this case. Yeah. Now we can visually see, right? I could put how many more electrons into that orbital before it's full. I can only put 1 more, right? And then it's going to be full. I could also, to tie this into our friend quantum numbers, I can give the 4 quantum numbers for that electron. The n should be what in this case? The n should be 1, right? Because that is what the first number there means. The L in this case would be 0, as that's the only option for L, right? Because 1 minus 1 is 0. That tells us it's in an s orbital, which is good. My m sub L for this guy will also be 0, right? Because there's only 1 orbital. Basically, it's hanging out in that sphere. Now, my m sub s in this case would be plus 1/2 as it is spinning upwards. And that is typically the way that we put the first electron into the orbit with the upward spin, the positive spin. And that would be basically the 4 quantum numbers for that particular electron. Any questions on that there? All right, then let's go to the helium, which I jumped the gun on last time, but it has 2 electrons here because it's atomic number 2. Once again, we always come back and start at the top here. So again, we're going to roll into our 1s orbital, and this will now give us 1s2 in this case. And again, what this is saying is that we're on the first energy level, we're hanging out on the s orbital, and I now have 2 electrons in there. And we have a couple of options when it comes to our orbital diagram here, right? So we could put our electron, our first one in like normal. And then for our second electron, we could do it one of two ways. We could go upwards, or we can put it in downward. Would be really our other option here. Now, which way should we do it? There is a rule that we want to follow, which is known as Pauli's exclusion rule. And basically, Pauli's exclusion rule basically says that no two electrons in the same orbital can have the same four quantum numbers. So there is a rule that we follow, which is known as Pauli's exclusion rule, which essentially states that if you have two electrons within the same orbital, they cannot share the same four quantum numbers. So let's take a look at our two options here and see maybe if one violates this Pauli's exclusion rule or not. Obviously here, if we shoot our four quantum numbers here for our first electron that went in, it's pretty much these right here, right? Just the exact same. So again, our first electron, n is equal to 1, L is equal to 0, M sub L is equal to 0, and M sub S is equal to plus a half. What would be my four quantum numbers for this one? N should equal 1. Again, it's still on the first energy level. It is still in the s orbital, which means it has an L value of 0. It has an M sub L value of 0. And what would the spin on that one, the way I drew it, be? Plus a half, right? Do these two electrons have the same four quantum numbers? And they're in the same orbital, which violates Pauli exclusion rule. So we will not do it that way because, again, that will violate that rule. So to get around sort of Pauli's exclusion rule, we actually put the second electron heading in the opposite direction, the downward direction, and that's going to change it, not greatly, but enough that the n value on this is going to be 1. The L value is still going to be 0 because it's in the s orbital. The M sub L value will be 0. And the M sub S value, though, in this case is, since it's pointing downwards, is not plus a half, but it is minus a half. So the difference in the spin quantum number is what allows two electrons to share the same orbital without violating Pauli's exclusion rule. Question? No, so it applies, Pauli's exclusion rule applies to individual orbitals themselves and how the electrons are sort of placed into those individual orbitals within the atom. In the entire atom, there's lots of electrons, right? Lots of orbitals on different energy levels, and they have lots of spin, all of them. And in some cases, their spins will cancel each other out depending on which way they're spinning. In other cases, they will all kind of maybe be spinning in the same direction and stuff like that. So you have to take into account if you're kind of looking at the overall atom in terms of its spin, which is sometimes referred to as being paramagnetic or diamagnetic. You have to look at all the sort of electrons that are involved. But this rule is specifically for individual orbitals and the electrons within them. Yeah. So in this particular case, what the difference is here again is that spin quantum number. And this arrangement, as I just mentioned a second ago, is what is sometimes referred to as being paired spin. They essentially, for the most part, kind of cancel each other out in terms of their spin. One goes positive, one goes negative, and essentially they cancel each other out. And that's what it's referred to as having paired spin. All right, then let us continue on here. Some electron configuration orbitals. We did helium. Let's go number 3 there, which is lithium. Lithium is 3 electrons. Again, it has 3 for its number. We will again start up here. And as we saw, we'll go to our 1s. We filled our 1s, which means we now need to come back through and hit the next orbital, which is going to be our 2s in this case. So this will give us a 1s to 2s1, Once again here, no dashes, commas, or anything like that in this case. By the way, in this case, I have how many electrons on the second energy level? Yeah, just one, right? And on the first energy level, I have two, right? So I have those again, first and second energy level in this case. We're going to do our orbital diagram. In this case, we would need a couple boxes. I am going to go side by side. It is not perfect for energy, really, but it is maybe more space saving than going upwards. If you're going to draw this based on energy, you would obviously put the 2s orbital box above the 1s orbital, but just to kind of save space, I'm going to go side by side. But once again, you would probably want to put it up here if you're kind of doing it based on or trying to show the energy. We're going to fill our first one in the upwards position, our second one in the downward position. That then cancels out, and now we're full, and now we're going to go to our next one and fill this one once again in the upwards one. The 4 quantum numbers for this electron, n would equal what in this case? 2. L would equal? You have a choice in this case, right? L can now equal 0 or 1. Can it be both numbers in this case? The answer actually is no, because my electron's in what orbital? Yeah, so specifically, that is what the 0 represents. This represents a p orbital, and it's not in a p orbital. So really, if we were doing it for that electron, the only value of L you could have would be the 0, because we're specifically talking about that electron in the s orbital. That also means because our L value is specifically 0 here, our m sub L value would be 0 as well, and our spin quantum number would be plus 1/2 as it's heading in the upwards direction there. Any questions on that one there? Let's then continue to roll here a little beryllium action, which is 4 electrons. Once again, we're going to start at the top here. So we could go to our 1s, we're back to our 2s. And as we can see in our picture, we do have room in that 2s for one more electron. So this is going to be 1s2, 2s2. This now means I have 2 electrons on the second energy level, and I have 2 electrons on the first energy level as well. In terms of my orbital diagram, once again, I'm just going to draw side by side instead of upwards. We're going to go up, down, up, and down. At this point, I cannot put any more electrons into that 2s orbital. If I have more electrons at this point, I now need to follow my little arrow and come back this way. And now we're going to hit into the 2p orbitals next to fill that up. Any questions on that so far? When we do that, we get that going into boron, it looks like. Boron's number 5 there, so it's got 5 electrons. Again, starting at the top, we would have 1s2, 2s2, and now 2p1. If you count up all the top numbers, that is how many electrons you place in there. 2 and 2 is 4, plus 1 is 5. How many electrons on the second energy level now? It is how many? It is 3, yeah. These are both on the second energy level, and on the first energy level, we still only have 2 in this particular case. Again, doing the orbital diagram, not correct for energy, but side by side for space saving here. We would actually need 3 boxes for our 2p subshell, right? And we're going to go up, down, up, down. First electron goes into the left there, also pointing in the upward direction. Now take a moment here and decide what are the 4 quantum numbers for that electron. So take a second and see if you can figure out the 4 quantum numbers for that particular electron. All right, so let's take a look, see how you're doing. So my n in this case should be 2. Yeah. That means my L values are 0 and 1. Are they both correct, or which one should it be? it should be 1 in this case, since we're specifically talking about the electron in the p orbital, as 0, right, represents the s orbital, but the 1 here represents the p orbital. So it has to be 1 for L only, not 0 and 1, because we're not talking about any electrons in the s orbital in this case. Now, the m sub L in this case, because it is actually an L value of 1, you do have 3 options of -1, 0, and +1, which again represents basically your px, py, and pz orbital. Is it all 3 numbers or just one of them? It is actually just one of them because it's specifically in only one orbital at this point. And the easy thing is it kind of just goes in the order how you do that. So it's actually in -1 in this case. So that's the nice thing. If you draw the boxes for the orbital diagrams, you do like the -2, -1, 0, and so forth. Just write them left to right the same way, and that will represent the orbital. So really, in this case, we have 1 electron in the px orbital is essentially what we got going on here. It is obviously going in the upwards direction. That means the m sub s here is going to be +0.5 in this case. Yeah. Any question on that there? All right, so continuing on here, number 6 on the periodic table is carbon. So we'll go number 6 here, which is carbon. Again, we're going to start at the top of that chart, which is 1s2, 2s2. And because we're into the 2p subshell, right, it does not get full until we have put in there 6 electrons. We've only put in 1 so far, right? So we got room for 5 more electrons. So we will stay at the 2p2. Once again, if you add up the top numbers there, 2, 4, and 6. Coming to our orbital diagram here, we got our 1s, our 2s, our 2p. We got up, down, and now we put our first electron there, and there is another rule that sort of helps us understand or choose where we should put the next electron. And that next is sort of important rule, kind of like Pauli's exclusion rule, is what is sometimes referred to as Hund's rule. And Hund's rule says the most stable arrangement of electrons in a subshell is to maximize parallel spin. Now, parallel spin is everybody heading in the same direction. We saw earlier paired spin is like that. So what that tells us is we would not want to pair off there in the first one because that obviously does not maximize parallel spin. That means when we have a subshell that has multiple orbitals, which is pretty much what the definition of a subshell is, we actually will put in the electrons one at a time in the upward position, as that will maximize pretty much parallel spin. So you'll go one at a time until you get to the end, and then you will flip back and come back through the same way, pairing off the spins. So you want to go one at a time and come back and pair off spin. Yeah. Yeah, it provides a more stable arrangement is by maximizing sort of the parallel spin. And we'll see some of that, for example, when we talk about a couple of exceptions to the electron configuration sort of rule. And that's sort of what happens to kind of maximize parallel spin. And it's just a better sort of stability arrangement for the particular atom. All right, so again, we would want to go one at a time and then come back and pair up. Since we're already halfway through the first 10 here or more, so we'll finish the first 10. Nitrogen, which is 7 electrons, we would go 1s2, 2s2, 2p3. By the way, let's actually do the quantum numbers for this guy before we go too far. N is equal to 2 in this case. L would equal 1 as it's in, again, the p orbital. M sub L in this case is going to be, again, -1, 0, +1. So it's hanging out in the 0 for our M sub L. And our M sub S here would be +0.5, right? All right, so now coming to our orbital diagram for our nitrogen, 1s, 2s, 2p. We'll go up, down, up, down, up, up, and up. At this point, we have nowhere to go up anymore, right? And we obviously cannot go up because it will also violate Pauli's exclusion rule, right? If we start putting electrons up and to pair them off with or put them in the same orbital. So we do have to kind of go in the opposite direction at this point. Looking at our quantum numbers for this one here, n is going to equal 2. L will equal 1 because it's in a p orbital. M sub L, again, it just goes in order. -1, 0, +1 will be in the +1 orbital, or the pz orbital, basically. And our M sub S also going to be +0.5 in this case. Any questions on that one there? So you can see you can get very specific about the quantum numbers and the electrons that are in an atom. Our orbital, we're going to go 8, which is oxygen. So 1s2, 2s2, 2p4. Again, if you count up the top numbers, 4, 2, and 2 is 8. Going to give us, in terms of orbital diagram here, we're going to go up and down, up and down, up, up, up. We now come back over and go in the downward direction here for that last electron putting in there. So what are the quantum numbers for this electron here, the very last one? N should equal 2. L will equal 1. Still in a p orbital, right? M sub L in this case is now back to -1, right? Because it's back to the guy on the left there. And our M sub S is going to be -0.5 as it's pointing again here in the downward direction. Yeah. Any questions on that there? And then sun, but fluorine over there next, number 9. Just brought my sunglasses. All right, number 9 here. 1s2, 2s2, 2p5. Again, counting up the top numbers, 5 and 2 is 7, plus 2 is 9. Doing our orbital diagram here. You can go up and down, up and down. Once again, up, 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 down, and now down there in the middle. And if we look at the quantum numbers for our last electron we put in there, once again, N is still going to be 2. L will still be 1 because we're still in a p subshell. Our M sub L, we have now moved from -1 now to 0 for that guy because it's in the center. And the spin is also down as well. And lastly here, neon, which is 10. We'll do 1s2, 2s2, 2p6. That is now going to fill up our p subshell in this case. And a little bit of orbital diagram happening here. So up, down, up, down. We're going to go up, 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 down, down, and lastly down. Taking a look at our final electron that gets into that subshell that fills it up. We got, again, our N is equal to 2. Our L still equal to 1 because it's a p orbital. It is now moved to the very last individual orbital over here, which is +1 in terms of that, right? And our spin is going to be -1/2. Again, that is what's going to give it a different set of quantum numbers than the other one occupying the same orbital. Any questions on that there? Okay, so why don't you do, why don't you do calcium, which is 20? Why don't you write the electron configuration for it? Why don't you also give the 4 quantum numbers for the, I don't know, let's do for the 16th electron that goes in. All right, let's take a moment. You don't have to do the orbital diagram. You can just write the electron configuration and figure out the 4 quantum numbers for that 16th electron. Okay, let's take a look. So again, we're going to start at the top there. So I'm going to go 1s2, 2s2, 2p6. That is 10 if you count up the top numbers. After again, we roll through our 2p6, we're now going to roll into our 3s2 in this case. So we can go 3s2, which gets us to 12. We then would go 3p6, which would get us to 18. And again, remember that as we talked about, after we go 3s2, we're coming this way to 3p. We are now going to 4s here next, not 3d. So we're actually going to 4s2 should be the proper electron configuration. That means in this case, we got how many electrons on the 4th energy level? 2. Yeah, got 2. How about on the 3rd energy level? How many we got going on? Actually, only have 8. Yes, and also 8 on the 2nd energy level at this point, and 2 on the 1st energy level. Right. Now we're looking for what is the 4 quantum numbers for the 16th electron. So if I just count up the top numbers here, that is 2, 4, 10, 12, 18. So I do know that my 16th electron, right, should be in my 3p subshell, right? So visually, if you want, you might just want to draw maybe the orbital diagram for just the 3p subshell and see what you got going on. So if I did that, it's a p subshell, which means I should have 3 boxes. And the way it should go in there, by the way, before we get there, we are at 2, 4, 10, 12, which means if I fill this properly, 12, this would be 13, this would be 14, this would be 15 as they go in one at a time, right? And number 16 would be right about there, right? So that should be my 16th electron. And now that I know that, my 4 quantum numbers, my n should be which number? N in this case is quantum number 3, yeah, since it's on the 3rd energy level. L in this case, because it's 3, could be 0, 1, or 2. Which one is the right number there? It should be 1 because it's in a p orbital, so it cannot be all 3 because we're specifically talking about that circled electron. So once again here, our L value would be 1 because we're talking about the p orbital. Our m sub L value would be -1 as it's sitting in that subshell basically. And our m sub s in this case would be -1/2. Yeah, so those would be our 4 quantum numbers here for that particular electron, which was the 16th one we were looking for. And again, visually, sometimes it's helpful maybe just to draw a little section of it and put the electrons in the proper way so you can visualize maybe what's going on. Yeah. What's that? There is a 3D, but the order at which happens when you get a lot of electrons in is the 4s orbitals are actually lower in energy than the 3D. So as the electrons go in, they will fill here and then start filling the d orbitals. And as we'll talk about, a weird thing sort of happens as well. Once they actually start filling, they actually switch in energy, and the 4s actually becomes higher in energy than the 3D. But at the beginning, when the electrons are going in terms of their filling, the 4s orbital is actually lower in energy than the 3D. Yeah. Yeah, so as soon as you would fill up, for example, which we did here, if we had any more, we would get into, for example, the 3D. So for example, if we did iron, right? Iron, which is 20 something there, 6, I think, right? I think. So this is basically up to 20, right, that we had. So we would go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And now if we look back on our little chart here, once we did our 4s, now we're going to hit the 3D and start filling those guys in. And now we'll have, where am I at there? 3D6 in this case. And that is the electron configuration for iron, which is a transition metal, and that's typically where you get into those d electrons. But because the s orbitals are lower in energy, as they fill, they will fill those guys first. Other questions? Now, speaking of that, when we do look at either of these electron configurations we just wrote, if we just look, for example, up through here, that is how many electrons up through here? If you count up the top numbers, how many electrons? Not everybody at once. 18, I hope, yes. So we'll go with 18 electrons, right? So 18 electrons there. Just want to make sure I wasn't in here alone, I wasn't talking to myself like a bad day. So 18 electrons, when we look at the periodic table there, right, is what element? Oh, I hope that's AR over there, a little argon. So we could do sort of a shorthand, if you will, and you could write the electron configuration as argon 4s2. The argon is basically representing this part of the electron configuration. Actually, for our iron one that we did as well, you could do that same deal. We come up through here. I'll try it again. That's how many electrons again? That is, thank you. Oh man, I'm supposed to start calling on people. I don't know. I see 18 electrons. Probably not. Or you can relax. You don't have to leave. It's okay. We have argon again for that, and then we just continue on the configuration here. There we go. And this is what is sometimes referred to as shorthand, or some people might call it noble gas configuration, because technically what should go in the bracket is always somebody from group 8 on the periodic table, and that is group 8 is a noble gas. So basically, you can put the noble gas in a bracket. The noble gas that comes right before the element you're writing the electron configuration for, and then just continue on with the electron configuration like normal. So for example, if we were doing sodium, which is 11, 1s2, 2s2, 2p6, 3s1. Once again, if we come through here, third time's a charm. How many electrons is that? That is 10. There you go. And on the periodic table, 10 is neon, right? So that's going to represent neon's configuration. So we could go neon 3s1, right? Would be sort of a shorthand way of doing it. But it must always be a noble gas from group 8. So helium, neon, argon, krypton, those guys at the very end of the periodic table. And it has to come before, obviously, the elements you're doing. Yeah. Why do you have to do it that way? You don't have to do it that way. It's just a kind of shorthand that is sometimes used for electron configuration. So you could write it out as 1s2, 2s2, and so forth, but sometimes you will very commonly see it sort of written in that shorthand notation. Because obviously as you get towards the middle, there's a lot of numbers and letters to write. So sometimes people just want to kind of do a shorthand of it, and that's where it comes from. There's no necessary benefit of doing it one way or the other than it's oftentimes used as well when people write it. But it does have to be, like I said, that noble gas that comes before it. Any questions on electron configuration, how it ties to quantum numbers, any of those things? Yeah. So clearly you need to be able to, as I mentioned, be able to write electron configuration properly. You need to be able to draw orbital diagrams properly. You need to understand those couple of rules we talked about: Hund's rule, Pauli exclusion rule, and obviously how quantum numbers obviously be able to do those and how it ties into electron configuration. All right. All right, so we kind of bounced around, but we kind of did a bunch of this here, maybe. There you go. All right, so we kind of did this one, n equals 3. Obviously, if our n equals 3, remember, your n could be 1 through 7. Your L can be 0 to n minus 1, which means, obviously, in this case, we would have 0 to 2, which means possible values would be 0, 1, and 2 for this particular one here. And obviously, since it's on the third energy level, the 0 represents an S, 1 represents a P, and a 2 represents a D, as we've been talking about. Now we also came across this one as well for L is equal to 2. Remember, for every value of L that you could have an individual kind of run of M sub L values, which again really represents the orientation of those orbitals in three-dimensional space is really what it tells you, but it also tells you really how many individual orbitals you have going on there. And again, if you were doing something like orbital diagram and you had to draw your kind of D subshell here, each of these would just go kind of in the order. So if you had to figure out your quantum number and you kind of did your orbital diagram and you had, again, that arrow there, it should have an M sub L value of -2 versus if it was over here, it would have an M sub L value of +2 and so forth. All right, let's see here. Go that we talked about last time. We saw those wonderful animations. We talked about spin again and Pauli's exclusion rule. We talked about that. So I don't worry too much about that there. And again, this is again why we have sort of the different orders of our shells as we kind of go through it based on how distance they are from the nucleus. All right. All right. We're going to talk a little bit about the periodic table. Before we get there, I'm going to talk about a couple other things first. And the off-ball principle is another principle that we basically were following that kind of ties in here. And the idea here is just like in atoms, basically protons are added one at a time. So are electrons. So electrons are added to the atom basically one at a time, as we were doing basically lowest energy to highest. Obviously, you need to fill whichever one's the lowest first until you continue on. Also, it should be said, obviously, that you do not need to fill a particular orbital completely or a subshell completely. Again, you just need to put the electrons in the proper spots. All right, we did our electron configuration, we did our Hund's rule, and we did our orbital diagram. All right, so let's talk a little bit about valence electrons. Valence electrons are the electrons in the outermost energy level. And you can find the valence electrons a couple of ways. You can find it by writing the electron configuration. So we go 1s2, 2s2, 2p6. That is our friend neon, which is 10 if you count up the top. We have 2 electrons on the first energy level. These are what are sometimes referred to as core electrons. These are closer to the nucleus, held a lot tighter, not involved in bonding. These electrons over here, though, which are on the higher energy level, we got 6 there and 2 there, gives us our 8 valence electrons. Those are the higher energy level electrons. Those are, as you may be familiar with, the ones that are involved in bonding. So one way you can figure out the number of valence electrons, which is an important thing, especially in the next chapter when we talk about bonding, is by obviously writing electron configuration. Nobody really wants to do that most of the time, so that's why we have a periodic table hanging on the wall. And the periodic table will tell us the number of valence electrons, and it is equal to the group number. So a reminder that groups go up and down on the periodic table, and we do use the representative numbering, which basically goes group 1, group 2. We skip the middle here in terms of numbering, 3, 4, 5, 6, 7, and 8 coming down. So you can get the number of valence electrons by just simply looking on the periodic table and seeing what group they're in. For example, that is neon's configuration. If we look at the periodic table, neon number 10 up there is all the way to the right, which is group 8 on the periodic table, and it will have 8 valence electrons. Just like lithium, which is over there to the left, that we did its electron configuration earlier, 1s2, 2s1. That is its 1 valence electron in the case of lithium. And that is its 2 core electrons in the case of lithium. And lithium is in group 1 on the periodic table, and it will have 1 valence electron. So the number of valence electrons does equal the group number. It also equals the group number for the guys in the middle, which are transition metals. But when we use those numbers, we actually use the 1 through 18 numbering for those guys. And when you're in the middle here, and you want to do valence electrons for the guys in the middle there that we skipped, we go 3 through 12 there. Make my periodic table a little bigger. There we go. So that middle part, which is here, we actually use the 1 through 18 numbering, and that will equal the number of valence electrons that those guys could technically have. So you take something like zinc, it technically has 12. Take something like iron that we saw earlier, it has 6 valence electrons. I'm sorry, 8 valence electrons over there in group number 8. All right, so let's talk a little bit about electron configuration and the periodic table here. So on the periodic table, we have groups which we use our representative numbering of the A numbering, as you can see here, where again we go 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Even though technically that is a number you pretty much use in all chemistry classes, most people don't use the A part of it. They just call it group 1, group 2, group 3, group 4, but they are usually representing the A numbering. There's also sometimes B numbering, as you can see on this periodic table, and you could also see just straight up 1 through 18 as well, which is also very common. So as I was mentioning a second ago, when you're doing in the middle section here, which are the transition metals, again, iron would have 8 valence electrons, 10 valence electrons, 5 valence electrons. You would use that kind of 1 through 18 numbering for that center section, but the A numbering for everything outside of that center section if you're doing valence electrons. So when we look at the periodic table, again, groups go downward here, our groups. And there's also periods that go on the periodic table, again, left to right. And there are 7 such periods on the periodic table. If you go group 1 and 2 on the periodic table, that is your S group. If you go group 3 through 8, that is your P block on the periodic table. If you go your transition metals, which are in here, that is your D block. And the 2 rows are typically on the bottom are your F block here. Now, for example, let's see how this would work. Let's just say we wanted to do calcium, which we did right here, right? And we wanted to count off the electron configuration for calcium on the periodic table. We would start up here at period 1 and go all the way across to helium, and that is 1s2, right? By the way, the S block has 2 boxes, and you can put how many electrons in the S orbitals? 2 maximum, right? The P block over here has 1, 2, 3, 4, 5, 6, and you can put 6 electrons in the P subshell. The D block here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you can put 10 electrons in the D subshell. You could trust me, but count all the way across here, you got 14 boxes going across there, which is how many electrons you could put in the F orbital. So if we're going to our guy here, calcium, this would be 1s1, 1s2 to there. We're now on period number 2, 2s1, 2s2. We're still on period 2, 2p1, 2, 3, 4, 5, and 6. So we have a 1s2, a 2s2, a 2p6. We're now over here to period 3, 3s1, and 3s2. 3s2. Now we're still on period 3 here, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. I'll go underneath as I run a room. And now we're on the 4th. This again is 4s1 and 4s2. So you can count off the electron configuration from the periodic table if you know what you're doing and you don't screw it up. That is because, let's say we're going to do iron, which we also did, right? So let's say we want to do iron in this case. I'll just clear up everything here. So let's say we're going to do iron, which is right there. All right, same thing. This is going to be 1s1 to here, which is 1s2. This right here will now be 2s2. This will be 2p6 to the end. This will be 3s2 here. This will be 3p6 to the end. This will be, again, our 4s2. And now we're at D, which is in this area, right? All this is D, basically. That is D1, D2, D3, D4, D5, and D6. What D is it, though? Is it 4D? It is 3, because that's where the D's start. So this guy here is not 4D. That is 3D. Underneath is 4D, 5D, and 6D coming this way. So this would be 3D, whatever I just counted there, 6, I think, right? 1, 2, 3, 4, 5, 6. 6. So you have to be careful. The D's are 1 behind the period number. Yeah? So the period there is 4. They start at 3. You also have to be careful down here in our F zone, because F start at what energy level? Start at the 4th energy level. That's 4F there. And that really should be in the periodic table right about there, which is actually period 6. And it's actually 2 behind the period number when you get to F. So again, the middle section can be a little tricky to sort of count off if you're not really careful. If you go with the little chart, you should be in good business for most of the problems that you would have. Any questions on that there? All right, so let's take a look at actually one more thing here. So let's talk a little bit about transition metals. There are a couple of exceptions, as I was talking about earlier, and 2 main exceptions to electron configuration happen in period 1 of the transition metals, and that is chromium and copper. And chromium and copper have an electron configuration. Chromium is 24 and copper is 29. And if you followed the zigzag sort of thing that we had going on there, you would end up with an electron configuration basically of argon 4s2 3d4 and argon 4s2 3d9. Once again, argon representing the first 18 electrons, 1s2, 2s2, and so forth. Now, the exception is it's been found experimentally that actually each of these guys are a lot more stable with 1 extra electron up in the d orbitals than they are in the s orbitals. And that is super easy to achieve because these guys, by the way, in terms of energy, are super close to each other. So it's not super hard for an electron to find its way up there. They're really close to each other. And in fact, as I mentioned earlier, they do switch at some point once you start filling the d orbitals. So the correct electron configuration for these guys is what we see down here. It should end up being argon 4s1 3d5. What does that essentially do for the s orbital and the d orbital? Well, it kind of maximizes parallel spin a lot, right? So we got a lot of kind of parallel spin happening in those orbitals. And in case of copper, argon 4s1 3d10. Same idea, we got that extra electron up there. In fact, if you go on the periodic table where both of those are located, chromium and copper, and you go down on the periodic table and in, there's a ton of exceptions like this or similar to this. Silver is an exception. PD is an exception. Actually, with PD, it has no electrons in the S. They've all been sort of promoted up to the D. So there's a lot of kind of exceptions underneath those on the periodic table in that transition metal region. For us, though, you will be responsible for chromium and copper to write the correct electron configuration. For everybody else, you could follow the little chart. And even though, again, it's technically wrong, as you can see here on some of these, we'll go with it. But for us, you'll just be responsible for chromium and copper. But as you can see here, as I mentioned before, the PD here has no more electrons up there in the S. They've all been kind of promoted up there to the D orbitals. And it's just sort of been found experimentally to be more stable. Any questions on that there? All right, we will wrap that up here for